Hello everyone and welcome back to Unit 5, Physical Behavior of Matter, where we'll specifically be focusing on gases. So today we'll be talking about ideal gases. You guys will be able to know the difference between real gases and ideal gases based on the kinetic molecular theory that we learned today. And then we'll talk about the ideal gas law, and you guys will look at the equation and you'll be able to calculate different variables for the gas using that equation. Now, kinetic molecular theory is the theory out there that explains the behavior of gases. Now, as the name indicates, we have kinetic in there, just like kinetic energy, which is the energy of motion or movement. So kinetic molecular theory, for the most part, explains the behavior of gases based on the movement of the gas particles. And there are four postulates or 4 points of this theory. The first point is that the gas particles are always in motion, and they are always moving in straight lines. And when they are doing that, yes, they change their path when they collide or hit the walls of the container or another particle. Just like if you look at this picture when the particles are not moving, and let's look at this particle right here. Let's say this particle is moving, it will go ahead and collide with the wall of the container. Now it will change its direction, it will bounce back, but even when it has bounced back, it will still move in a straight line. And then it will continue doing that, hit the wall again and change its direction, but still move in a straight line. Then hit the wall again, change its direction, but still move in a straight line. And as I said, this doesn't always just happen with the wall of the container. Sometimes the particles just collide with each other. They change direction, but continue moving in straight lines. The second postulate says that when that collision happens, when we have a particle that is colliding with the wall of the container or with another particle, there is a transfer of energy that takes place. But the energy is only transferring between those two things, between those two particles or between the particle and the wall of the container, but no energy is lost. This type of collision is called elastic collision, when the overall energy of the system remains the same, because they're just like transferring their energy from one thing to the other, but not losing anything. The third postulate of this theory talks about the volume of gases. So what it says is that if you put, just like in this picture, if you put a gas in a container, the particles, the gas particles, are super far away from each other, and there's a lot of empty space between those particles. So basically, when we can just say that the gases have no volume because their particles have so much empty space between them that we can just say that we can ignore their volume, and gases have no volume at all. And then the fourth postulate of this theory says that because these particles are so away from each other, they have so much space, so much distance between them, they don't really have a lot of attractive forces. And as we discussed in the previous topic, those attractive forces are called the intermolecular forces. So this fourth postulate says that gases basically don't have any intermolecular forces between their particles. Now, the problem is that this theory only explains the behavior of ideal gases. That in ideal gases, all of the particles will be so away from each other that they'll have no volume, they'll have no intermolecular attractions, they'll always be moving in straight lines, and there will always be elastic collision, that they'll transfer their energy between each other. But when we compare this ideal gas behavior with the real gases that we see in this world, it turns out that the first two postulates are pretty much always true, because that happens in real gases as well. But the last two postulates, postulate 3 and 4, are not quite correct, because real gases deviate from these two postulates. So if you look at this picture now, remember postulate number 3 said that gases don't have any volume because their particles have so much empty space between them. Now this, if we just change the situation a little bit, and now we have the gas in the same container, but let's say we apply pressure on that. And remember the concept of compressibility when we said that we have if there's a lot of space between the particles, we can apply a lot of pressure on that thing and the particles will start moving together. So if we do that thing with these gases, if we apply a lot of pressure on them, the particles will start to come together, and then there will be a point where ideally, let's say if we can just assume that we can get all of those particles together at one place, organized in this small space at the bottom or on the side of the container, then that will be the volume of the gas, because these are the gas particles now. Now they don't have any space between them. It's just those particles. Then this will be all the space that is being taken right now by these particles is the volume of the gas. So that's how we can say that the third postulate is not quite correct, because the volume of the gas is significant. We cannot just say that we can ignore their volume. They do have some sort of volume. And then this fourth postulate, which said that they do not have any intermolecular forces at all. Well, if you do the same thing, now we are applying the pressure, the particles are coming closer and closer together. So remember we said that intermolecular forces are the attractions between the particles. The closer they are, the stronger the forces are. The farther away they are, the weaker the intermolecular forces are. So now that we are pushing those particles together, they are going to have intermolecular forces. And even when in the gases those particles are super away from each other, they do have some sort of, maybe very slight, maybe very few, but they do have some sort of attractive forces between them. So we can't just say that they don't have any attractive forces at all. Yes, they are weak, but they do have some attractive forces. So that's how kinetic molecular theory is not super or 100% correct, because real gases do not always have no volume or no intermolecular forces. Now, if we compare the ideal gases and the real gases side by side, we can say that ideal gases exist under very low pressures and very high temperatures, because during these two conditions, the particles are super far away from each other. If you don't have a lot of pressure, the particles have a lot of empty space between them, and same thing with the high temperature, that now the particles are moving at a very fast speed, so they don't have time to like stay at one place and feel those attractions and like be close to any other type of particle. But the real gases, on the other hand, exist at high pressures and very low temperatures, because if we have very high pressure, now we are bringing the particles closer and closer together. And when we have low temperatures, the particles are moving slowly. They are not at that speed. They do have time to like stay at their place for like a little bit and have those attractions with other particles around them. So in real world, we only hydrogen and helium are the two gases that behave most like ideal gases, which means their volume is quite negligible or quite insignificant, and they don't have a lot of intermolecular forces. Now, gases have four different variables or characteristics, we can call them. The first variable is temperature, which is represented by T. The second is pressure, how much pressure we are applying, which is represented by P. The third is volume, how much space are those gas particles occupying, which is represented by V. And finally, the amount of gas, which is represented by this lowercase letter n. Now, this is also called mole. We'll talk more about the moles in a few chapters, but for now, just know that mole is whatever quantity or amount we have of something. So in this case, n will be representing the amount of gas in moles. Now, if let's say we know three of these characteristics or variables, and the fourth one is unknown, there's an equation called the ideal gas law that we can use to calculate that fourth thing. And this is how we write the ideal gas law. Now, just notice one thing here, that this n is supposed to be a lowercase n. So ideal gas law is PV equals nRT. Now, we won't get into the complication of how we got that law or how can we derive this equation. Just memorize this. This is ideal gas law, PV equals nRT. Now, in that equation, PV equals nRT, the P represents the pressure, and the unit that we'll be using for pressure for gases is, and for this equation specifically, is atmosphere. So if you're given something in kilopascal, we'll have to convert that to atmosphere. And remember, we have 1 atmosphere has 101.3 kilopascal. The volume, V represents the volume, and the unit that we'll be using for volume is liter. So if you are given the volume in milliliters, you'll have to convert that to liters. The amount of gas, N. The unit for amount of gas, as we said, is mole. And then the gas constant, the R in there represents the gas constant. Now, a constant is something that never changes. So this R value that you guys see here, this is always going to remain the same. And you will have to memorize this because this is not given anywhere in your reference table packet. So memorize the number or the value for gas constant, which is R, that's 0.0821. And please also memorize the unit for this gas constant. So that unit is liter times atmosphere divided by Kelvin times mole. Now, because of this gas constant, whatever units we see in there, that's exactly what we want to use for our variables as well. For example, the unit here that we have for volume is liter, so that means we want to make sure that our volume is in liter. If it's not given in liter, we'll have to convert that to liters. The atmosphere, we want to make sure that our pressure is given in atmosphere. If it's not, we'll have to convert. Kelvin, we want to make sure our temperature is not in degrees Celsius, it is in Kelvin. And then finally the mole, moles will always be given in mole, at least for this chapter. And then the temperature is represented by T, and the unit that we'll be using for temperature is Kelvin. So let's look at a few problems to use that equation. Now this problem right here says that we have 2.5 liters of a gas in a container. The amount of that gas is 0.46 moles, and it is at 315 Kelvin. What is the pressure inside the container? Now, just like we do any problem in chemistry, the first thing that we want to know or write down is what's given. So we are given the volume of this gas, which is 2.5 liters. Liter is exactly the unit that we want, so we'll leave it like that. The amount of gas is given 0.46 moles. Moles is the unit that we want, so we'll leave it as that. Next up, we have the temperature in 315 Kelvin. Once again, we need our temperature to be in Kelvin, so we're good there. And then finally, we know that the gas constant here will be, which is R, it will be 0.0821 liter times atmosphere divided by Kelvin times mole. Now, we need to know, what do we need to find? What's unknown? What's the question asking for? So that is the pressure of this gas. The equation, based on all of these variables that are given, we know that the equation that we can use to calculate this missing variable or missing characteristic of this gas is the ideal gas law. So that's PV equals nRT. All we have to do is plug in the numbers. Now, we need to find the pressure, which is on the left-hand side of the equation right now. We want to make sure that whatever we are finding out, that's the only thing that we have left on one side of the equation, and everything else is moving to the other side. Now, The only number or the only quantity that we see with the pressure on the left side is the volume, which is 2.5 liters. If we want to get rid of that 2.5 liter on the left hand side and we want to move that to the right side, we'll just have to divide that on both sides of the equation. So simple algebra rule. Whatever we want to get rid of, if that thing is multiplying with the other number, we'll divide it. If it's subtracting with the other number, we'll add it. If it's adding to the other number, we'll subtract it. So just whatever it's doing, we'll do the opposite of that. So now that we divide 2.5 liter on both sides, this is what we get on our right hand side. Now, very simple, just go ahead, put all the numbers in your calculator. 0.446 times 0.0821 times 315. Get your answer, divided by 2.5, and whatever answer you get, we'll get 4.76 atmosphere. Now, the unit for pressure is atmosphere, and specifically for this problem, when we are using the ideal gas law, the unit should be atmosphere. But the second way to double check it, or to make sure that you guys are doing this correctly, is to just cancel the units. So the first mole will cancel with the mole in our gas constant at the bottom. The liters will cancel with the liters in the denominator. The atmosphere is the only unit that will be left. There's no other atmosphere to cancel it with. And then our Kelvin will also cancel with the Kelvin. So the only unit that we're left with is atmosphere, which is the unit of our pressure. Let's look at another question. So now this question is asking how many moles of a gas should be placed in a 250 milliliter container at negative 24 degrees Celsius to produce a pressure of 202.6 kilopascal. First thing that we do, find what's given. So we are given the volume, which is 250 milliliter. Remember, that's not the unit that we need. So we want to convert that into liters. Now, if you guys look at table C, I believe, in your reference table packet, where you have all those prefixes, milli is 10 to the power of negative 3, which means it's 1 over 1,000. So we'll take 250 and we'll divide that by 1,000 to get 0.25 liters. And that is our volume. Next thing that's given is the temperature, which is in degrees Celsius, negative 24 degrees Celsius. We want to convert that into Kelvin. So same old equation given in table T. We take the temperature in degrees Celsius, add 273, and we get our answer in Kelvin. Next up, we are given the pressure in 202.6 kilopascal. Once again, we want to convert this into atmosphere. We need our pressure in atmosphere. So as we all know, 1 atmosphere is equal to 101.3 kilopascal. So what we'll do is we'll multiply this 202.6 kilopascal with that conversion factor. Now all that this conversion factor is saying is that 1 atmosphere has 101.3 kilopascal. That's it. The kilopascal cancel out. We'll just do 202.6 divided by 101.3 and we'll get our answer to be 2 atmosphere. The next thing that we know from theory is the gas constant, which is R, that's 0.0821 liter atmosphere divided by Kelvin mole. What is unknown? We are trying to find the amount of this gas, the number of moles. So the equation that we can use is the ideal gas law, PV equals nRT. All we do is plug in the numbers first. Now we have the number of moles, or the amount of gas, on the right hand side, and we want to make sure that's the only thing that we have on the right side, and we want to move everything else on the other side. So once again, our gas constant and our temperature is multiplying with the amount of gas, so we'll just divide it on both sides to get this, and then we'll just do the math. So 2 times 0.25, get your answer, divided by, in brackets, put 0.0821 times 249. get your answer. And that is going to be how many moles we have. So the amount of gas is 0.0245 moles. Alrighty, so that was it for this part of the unit, and I'll see you guys next time.